Okay, I guess able to see my screen here?
Yeah.
Okay. I'm Shamba Cotton, working in the aerospace industry for Collins Aerospace. Today, I would like to focus on audit and the certification aspects when it comes to the safety critical hardware and software. Certification is reactive. There are many aspects. We do have a DO 170BC compliance, which is traditionally audit driven. When we do it audit based, there are cases where we end up in late discovery of the defect, which could lead us to the costly rework across multiple artifacts. And traceability gaps when it comes to, we have these high level requirements and low level. When the testability, there are disconnected tool chains. Redundant verification, we want to do it just enough so that we're not duplicating the effort. So these are the issues we currently have, how using the AI and machine learning to overcome these issues. I'm going to cover that in my upcoming slides here. Introducing the zero findings certification. Here, I would like to shift from reactive to the proactive approach, understand what the risks we are having in our formal reviews, flag them, and then use the agile concepts like the continuous improvement, continuous monitoring, which would help us with the audit readiness maintained throughout the multiple phases of the stages of involvement. Intelligence driven would be the data and AI guided in every decision we have that would help us with the scalability at the large scale and also meeting the milestones to achieve in a competitive environment where compliance and the safety plays a crucial role. Why certification plays important in an aerospace industry? Because of the criticality associated with it. If there are any failures, which could lead to the catastrophic effect, which can be life-threatening to the passengers and the pilots involved. That's where it's very crucial to have that zero findings certification and have the confidence in the software we have built. How can we leverage the existing AI and machine learning concepts so that we can use that effectively to achieve the safety of the crew members? The first pillar is going to be the continuous compliance monitoring, where we're going to work on the real-time data gathering, automating the gaps, what we see when it comes to the verifying the artifacts we have. The second one is closed-loop traceability. Are we doing the top-down traceability, bottom-up traceability? That way, all the requirements, we are verifying it for the testability, and then also make sure the tests are all traced back to the requirements we have with the closed-loop traceability. Shift-left verification. Verification should not be happening at the end. It has to be in the beginning so that the early flagging, the defect prevention would be beneficial. These are the three pillars of the zero finding certification. Continuous compliance monitoring. As we are aware of the DevOps development where we are continuously monitoring the artifacts, providing the real-time feedback, health assessment, integrating them in real time with the advanced tool chains where it would auto-generate the code, some of the GPT styles, LLMs, and the BERT transformer. We can use these to auto-generate, and then the testability of it. These can, again, use to coverage or analyze the coverage gap, provide the requirement-based coverage, so that we have that meeting the objectives of the DO-178B. It goes through the very broader and narrowed objectives, so that we are emphasizing more on the safety of the passengers. Real-time alerts would help with these toolchain workflows, and the audit readiness. It would be audited internally, externally, and it would goes to the Federal Aviation Authority. Not just that. If it is an international flight, it goes to the EASA, European Board, and the Transport Canada, getting the approval from multiple authorities and the delegates. That's where it goes through the complex certification process to ensure we are meeting the compliance DO-178C objectives. Closed loop traceability, it's going to cover the requirement to test coverage, or every requirement we have, is it verified in real time, and disciplinary synchronization. How are we communicating with the other stakeholders, system, software, safety, quality, and having that traceability model. Evidence generation, this is where we could avoid the duplicate work and provide the coverage. That way, reduce the manual effort and provide the consistent traceability metrics and the coverage data. Shift left verification, again, how effectively we can use these natural language processing models. We can use LLMs, RAG, retrieval augmented based models to verify the requirements. And then there are ambiguity words we use. How can we avoid those using these AI and machine learning models? Moving the verification upstream, that's where we can reduce the cost and detect the failures early and provide the certification and the safety critical radio interface units, having that uplink and downlink, verifying those messages. Is it pilot communicating with the ATC ground station, from ATC ground station to the pilot, how these messages can be verified. Machine learning at the core, how are we going to train the model? This is where... Sure. Machine learning at the core, how can we train the model? The historical defect rate, the audit findings, artifact quality signals. These are the main inputs we would give to the AI and machine models to train them, so that they can risk the artifact which are at high risk. NLP driven requirements. This is mostly towards the appropriate, timely, where we can indicate that ambiguity at the source, which provides the constant feedback to the authors to improvise and gain the score of 4 out of 5. That's the score we are looking for these requirements. Intelligence test prioritization. How are we going to prioritize this? Prioritize on the high risk and high coverage, maintain this effort. When it comes to the low risk and low coverage, deprioritize and monitor them. Low risk and high coverage, that is where we need to work towards the reduction. Integration with the automated tool chains. These are the requirements. We have the DOORS, JAMA, and NLP. The models one would be the MATLAB and CI, continuous integration and continuous development. Having the integrated tools would help us to increase the speed and gain that competitive edge with the flight management system and the other functionalities. Agile delivery metrics. It is similar to the agile method. We have been following it. How can we integrate that with the AI and machine learning concept so that include the sprint execution and the risk gate decision and have that fed into the next sprint execution with the compliance check and the evidence package update. Measurable impact across the program, ensure the certification lifecycle is reduced, reduce the rework cost, and have the predictable program milestone can be achieved and gain the competitive advantage. Practical framework we can apply is go with the defect in history, apply it to the NLP and the requirement authoring, and connect that back to the traceability and evidences and focus on the shift left proactive approach. Any questions, concerns that needs to be discussed further here? Thank you all for joining.
Hello everyone, are you able to see my screen? I'll take silence as yes. So
I can.
cool. So good morning or good evening. I'm Bijo. I'm a senior applied scientist, and today I want to talk about a practical question that comes up in almost every ranking system. So, how do you get the reasoning power of large language models over signals that aren't text, like images, audio, like engagement, sensors, like without paying the cost of serving a giant multimodal model on every request? So the answer I'll walk you through is a pattern we call feature injection. So let's dive in. Um, So when it comes to the reality of modern ranking, you use a lot of different types of features. Like for example, and there are a lot of like different industries that use ranking, like e-commerce, search, music recommendations, and we can't just be limited to the query string. The query string and the product title are just the beginning. So the engine is fed with, like say, click-through rates, images, purchase history. Every one of these shapes what the user sees next. So the question isn't whether to use multimodal signals, like you really have to. And we really need to figure out like how to use them without like blowing up our cost and latency budget. So one of the approaches is an end-to-end multimodal model, like feed raw images, audio, but it doesn't really scale economically. So you need GPUs in the serving path, and the reasoning is a black box, and it's really hard to explain to stakeholders if needed. So feature injection really flips this. Specialist extractors can run upstream, offline, or in batch, and at serve time, all you have is text-only LLMs, no multimodal encoders in the hot path. So in our experience, that translates to like significantly lower inference cost and lower latency, and it works with any instruction following LLM you already have. So to be clear, multimodal models don't really disappear; they move offline. So where their cost is like really balanced out. So yeah, what's eliminated is like a multimodal compute per request. Uh, so feature injection concretely, it's basically it's a pipeline with like starts with raw features and you normalize the features, go about feature engineering. In simple words, what you're trying to do is you're trying to convert these numeric features to something that an LLM can understand. So let's take an example of a music track. So let's say the tempo is 128 BPM, danceability is zero point 0.9. So these are numbers are LLMs are like really not very good at reasoning over raw numbers. So, but if we instead of like raw numbers, if we inject this track has a fast tempo or BPM is top 15% of the catalog, like that's something which is more understandable to LLMs. So now with this type of input, the model can reason about it of in the same way a human would. Yeah. In the interest of time, I will move a little fast. Anyway, architecturally, this becomes like three cleanly separated stages. Stage one being like feature extraction, feature engineering, and then LLM reasoning. And here's what the production system looks like. Let me move to the next slide. Yeah. So let's make this a little concrete with an e-commerce example. So a search query comes in against millions of products. We use a smaller model or a smaller system to generate like some candidates that can be passed through the LLM, and then we enrich each candidate with injected signals like click-through rate or like the images or like signals from other modalities. And so why does this scale? The features are pre-computed and cached. The LLM only ever sees the top five, let's say 500 candidates batched into small groups per call. And it reasons over like feature summaries, not raw product images. Cost is linear and predictable. Yeah, the quality of the ranking depends critically on how you translate features into language. So three techniques have worked for me in the past. So for example, let's say CTR is 8.4%. So you can say something like 8.4%, which is top 5% of its category, or more of a contextual framing where anchor the task in the user. And yeah, or something like given that this user bought high energy workout gear in the last 30 days, ranked by predicted purchase likelihood. So, and one of the biggest benefits of this is that the LLM outputs also includes explainability. So if the product managers want to understand what exactly happened, it is much easier to do that versus like using a black box neural network. Yeah, so the cost control mechanism deserves its own slide, I guess. So because this is what makes the economics work. So stage one is a fast retrieval, and it scales to billions of items at like sub 10 millisecond latency. And stage two is LLM re-ranking over some of the top candidates. So your cost really scales with the candidate set, not your catalog size. Uh, yeah, pulling the benefits together. So mainly it's low latency, and when I say low latency, this is not really replacing some of the standard neural networks, which are much faster. This is when you want to use larger model to improve the quality of your recommendations, and sure, I'll do that. Yeah, sure. So. Let me skip through some of these slides. And this framework can be used across industries. And like one of the important pieces is that you need to know when to not use it. So like the system would struggle with raw perceptual details like image texture, speaker emotion, video aesthetics. So that type of solution, you would need actual image models or video models, and you can't rely on summarizing or like passing summarizations to language models. Yeah, skip through this. Now coming to the second last slide. So modern ranking is multimodal by nature. You can't compete on text alone. End-to-end multimodal models don't scale economically. And the two-stage pipeline keeps cost tied to candidate count and not catalog size, and uh, know the sweet spot. So use this when signals are summarizable and cost and interpretability matter. So use end-to-end models when perceptual fidelity is non-negotiable. Thank you.
All right. So let me know once my screen is visible. Am I audible?
Yes.
Okay. So I'll be talking about the securing the LLM-powered AI agents, trust boundaries, and the privilege control in the enterprise system. So my focus of this work is a practical enterprise security problem. As the AI agents begin to act on behalf of the users and the system, so they are no longer just the passive assistants. So they are becoming active participants with accesses, privileges, and the operational. So what that means is that the traditional application security and the traditional identity models are no longer sufficient by themselves. So I'll talk about these in details in the next slides. So at the high level, the challenge is that the agents are gaining privileged access to the enterprise system while the security model around them is still immature. So this stack highlights the 5 aspects of the challenge. Prompt injection attacks are increasing, traditional controls are not adapting fast enough. Agents use dynamic context-sensitive permissions. Existing trust boundaries are structurally weak, and IAM systems are originally designed for the humans rather than the autonomous non-human identities. So the trust card is the proposed response to that gap. It is built on the 4 integrated mechanisms: trust, context, separation, continuous behavioral attestation, dynamic privilege containment, and IAM integrated identity controls. So why AI agent security matters? So the problem matters because AI agents are already being deployed in the high-level and regulated enterprise models. The presentation point to financial services, healthcare system, cloud infrastructure, and DevOps are the AI examples where the agents are involved in the fraud detection, compliance automation, patient interaction record access provisioning, instant response CI/CD remediations. So what makes these agents different from the conventional software is not just automation, but autonomy under the natural language control. So they interpret language, make decision, access sensitive resources, and execute privileged tasks without uh, the guardrails or without any human identity anchor in the traditional sense. Okay. So the AI agent threat landscape. So the threat landscape is organized into the 4 categories: the integrated attacks, the confidential attacks, availability attacks, and the privilege or the identity attacks. So on the integrated slide, the presentation highlights prompt injection, context manipulation, and instruction hijacking. On the confidential slide, it includes the data extraction, permission discovery, and credential leakage. Availability attacks include resource exhaustion, agent abuse, and denial of services, while the privilege and identity attacks include unauthorized permission expansion, lateral movement, and the IAM token or the session theft. So this work makes three main contributions. The first, it proposes a formal trust context separation model that creates the mathematical isolation between the trust instructions and the external inputs at the inference layer. So second, it introduces the trust guard architecture, so which combines dual path processing, cryptographic verification, dynamic privilege containment, and IAM bound identity as a unified defense framework. Third, it reports the large-scale empirical validation across the financial services, healthcare, and the cloud infrastructure with more than 2.3 million real-world transactions. So the contribution I would emphasize most strongly is the shift from the heuristic prompt defense to formal trust separation. The argument is that if trusted and untrusted inputs are allowed to blend too early, security becomes probabilistic. If they are formally separated and verified before influencing the privileged decisions, security becomes much more enforceable and auditable. Okay, so moving on to the next slide is the trust card architecture overview. So in this slide, the input comes from the user devices and the IAM authenticated agents and pass through the multiple coordinated layers before reaching protected enterprise system. The key point shows here is that each layer has its own security objective and authenticates against the enterprise IAM. So failures are isolated and do not silently cascade across the environment. The architecture maps directly to the core goals like the integrity, the CIA track, which is integrated confidentiality, availability, and at least the privilege. The four major mechanisms are the dual path processing, behavioral attestation, dynamic privilege containment, and IAM bound identity. So with the interest of time, so I'm rushing through the slides. So the dual path processing engine is one of the most important design ideas in the presentation. Trusted context includes the system instructions, security policies, verified operator configurations, and IAM issued identity assertions. The untrusted context includes user inputs, external API data, or the third-party tools. The architecture enforces separation between these two paths before inference rather than trying to clean up the consequences afterwards. That distinction matters because many prompt injection failures happen when the untrusted content is allowed as the instruction bearing content. The trust cut claims is that if the trusted content is explicitly isolated and tied to the verified identity context, then the instruction corruption is much harder. Prompt injections is constrained. So once trust context are separated, trust guard add a form of verification gate at the every trust boundary crossing. The presentation describes three checks: integrity, identity and integrity validation, context verification, and temper detection. In other words, before information can be influenced as a privileged agent decision, the system confirms who originated it, whether it was altered, whether it begins in the expected trust scope, or whether there are signs of semantic or the structural manipulation. So the next mechanism is the continuous behavioral attestation. This slide presents the lifecycle of baseline monitor, detect and mitigate. The trust card monitors agent decisions and reasoning patterns, access request and privilege usage against the IAM entitlements, operational behavior drifts, and resource consumption anomalies. So what I would stress here is that the model assumes the compromise may still happen. It also relies on the rapid detection and response before the privilege actions are executed. According to this slide, anomalies can trigger automatic IAM session suspension. That is very important integration point because it means behavioral signals are not just locked in the application, they actually feed back in the identity enforcement and the access revocation. So this slide contrasts the traditional model of the persistent, always on the privileges with the trust card model of the request, verify, grant, and revoke. In traditional model, broader privileges may remain available across the entire session lifecycle, even when no longer needed. Trust card instead scopes the permission to the verified task, issues then just in time through IAM, and automatically revokes them after use. So this slide lists three key benefits: minimal exposure, reduced blast radius, and context-aware authorization. So this slide, is where the architecture becomes especially relevant for the enterprise security and the governance team. The trust card does not replace the enterprise IAM. It extends the IAM to support non-human autonomous identities. Each agent is provisioned as the first-class identity in the enterprise identity provider, such as Entra ID, Okta, or Ping, rather than hidden identity, a shared service account. So this work is not presented only as the conceptual model. This slide report the evaluation across 3 regulated industries with over 2.3 million real-world operation. So I will not. I will pretty much skip that slide to be in interest of the time. Security performance results. So this slide presents the comparative attack success rates, where lower is the better. Trustcard shows 4.2% for the direct injection, 12.8% for the indirect injection. 6. I'm about. Yes. Yeah, sure. So coming to the next slide, talks about the finding in terms of business terms. The next slide highlights the 94% attack detection, 3.8% false positive rates, and 11.2% performance overhead. So here, so I've split all the impact and the key benefits in terms of security, performance, enterprise, and operational cost. So the overall conclusion is the trust card addresses the 4 pressing problems today: prompt injection, context poisoning, privilege escalation, and agent manipulation. Thank you. Yeah. Any questions?
Hey everyone, can you able to see my screen? I'm audible?
Yes.
Okay. Good morning everyone. Thanks for joining the session. Today I'll be discussing how artificial intelligence is transforming telecommunication network management as network continues to evolve with technologies like 5G, edge computing, cloud native infrastructure. Managing them has become increasingly complex. In this presentation, we'll explore how AI helps network operators move from reactive management to predictive and autonomous operations. We'll look at applications of AI in predictive maintenance, traffic optimization, anomaly detection, and the evolution towards self-optimization network. So, the telecommunication industry is undergoing significant transformations. The rapid adoption of 5G, edge computing, and increasingly complex traffic pattern is creating new operational challenges. Traditional network management approaches are no longer sufficient to handle the scale and complexity. AI and machine learning models are becoming essential for maintaining service quality, improving operational efficiency, reducing cost, and building resilience network that can adapt in real time. So as of today, for today, this is the overview. We will begin by looking at the predictive maintenance, how AI enable earlier fault predictions. Next, we will discuss reinforcement learning for optimized network traffic in real time. Then we'll explore deep learning techniques for anomaly detection and proactive incident management. Finally, we will look at how these technologies contribute to AI native self-optimization network architecture. Let's begin with predictive maintenance. Traditionally, network maintenance has been either reactive when repairs happen after failures occurs, or scheduled at fixed interval regardless of equipment conditions. AI changes this approach by continuously monitoring network equipment and identifying potential failures before they occur. This allows operators to plan maintenance proactively, reduce unexpected outage, and improve overall network reliability. The goal is to move from reacting to failures towards anticipating and preventing them. This slide highlights the impact of AI-enabled predictive maintenance. Validated deployments have achieved 94.2% of fault predicting accuracy, helping identify issues before they become critical. Unexpected equipment failure has been reduced by 67%, while the mean time between failures has been increased by 43%, improved equipment reliability. Yep. Organizations have also reported 76% less unplanned downtime and a 52% reduction in maintenance cost by shifting from scheduled maintenance to the condition-based maintenance. These results demonstrate how AI can improve both operational efficiency and service continuity. So the next topic is advanced sensor architecture. Accuracy predictions depends on reliable data. That's where advanced sensor architectures play an important role. Modern monitoring system combines multiple data sources, including thermal, vibrant, and electrical signals, to provide a comprehensive view of equipment health. According to the results shows, 89% of the potential failures can be identified at least 48 hours in advance, while overall maintenance efficiency improved by 78.3%. Edge inference further reduced the latency by processing sensor data close to whether it's generated, allowing faster detection and quicker operational process. The next one is a reinforcement learning. So we'll focus on this. Unlike traditional routing method, reinforced learning continuously observe network condition and learn the best routing decision based on the performance objectives such as throughput and latency. As network conditions changes, the AI agent updates its routing policy in the real time without requiring manual interventions. This enables network to respond quickly to traffic spikes, congestion, and link failures, supporting more efficient and adaptive traffic management. Multi-agent reinforcement learning. Built on reinforced learning, the slide introduced multi-agent reinforced learning, where multiple agents work together across different parts of the network. Instead of relying on a single centralized controller, each agent makes local decisions while coordinating with other agents to achieve overall network efficiency. The decentralized approach improves scalability and eliminating single point of failure. As shown in the figure, this approach has demonstrated 85.6% network load prediction accuracy. Yeah. 23.4% of improvement in the resource utilization and 99.95 optimal path selection accuracy. These results highlight the potential of collaborative AI for managing increased complex telecommunication networks. The next area is the deep learning based anomaly detection. Telecommunication networks generate enormous volume of telemetry data every second. Detecting unusual behavior manually has become increasingly difficult. Deep learning models continuously analyze network telemetry to identify abnormal patterns that may indicate fault, performance degradation, and potential service disruptions. Rather than reacting after user experience a problem, the model enables operational to detect issues much earlier and take corrective actions before they impact network performance. The proactive approach improves operational efficiency while take unnecessary alerts. These slides represent the performance achieved using deep learning for anomaly detections. The model achieved 95.8% detection accuracy while maintaining a very low false alarm rate of 1.2%, helping reduce alert fatigue for network operator center teams. In addition, predictive incident prevents contribute to a 71.2% improvement in the service availability and 63.8% faster incident resolutions, and also 76.5% fewer service disruptions. These results demonstrate how AI not only improves the detection accuracy but also strengthening overall reliability and customer experience. So far, we have discussed individual AI capabilities. The next step is bringing the capabilities together to create autonomous network architecture. The version is to build networks that continuously monitor themselves, analyze challenging and changing conditions, and optimize operations with minimal human interventions. Instead of operators manually respond to every event, AI become an active participant in maintaining network performance, improve resilience, and support more efficient operations. This represents an important shift from assisting automated towards intelligent, self-managed network. These slides highlight four key technological support autonomous network management. The first is a closed loop automation, where network continuously sense, analyze, act without unnecessary delay. The second one is intent-based networking, where operators define the desired business outcome and AI determine how to achieve it. The third one is a federated learning, which enables distributed model training without moving sensitive network data to a central location, both supporting both scalability and privacy. Together, these technology move telecommunication network towards higher level of autonomous and continuous optimization. And finally, so we conclude, I like to summarize the key message for this presentation. Artificial intelligence is transforming telecommunication network management across multiple areas, from predictive maintenance and intelligent fault predictions to traffic optimization, anomaly detection, and autonomous operations. Rather than replacing network engineering, AI enhance decision making by providing fast insights, predicting issues before they occur, and enabling more efficient resource utilization. As telecom network continue to grow in scale and complexity, intelligent automation will become essential, capable of maintaining reliable, high-performing, and resilient service. Thank you.
Thanks, Nagappan. I'll go next. So my name is Gaurav Yadav, and I'm going to talk about hybrid architecture using FPGAs and ASICs for accelerating machine learning, where we use ASIC efficiency balanced with FPGA reconfigurability. So what is the acceleration imperative? Right now, the modern models, ML models, have outpaced the CPU GPU architecture that can be delivered cost effectively. The bottlenecks are actually structural and not incidence based. So for latency, there is a strict sub-millisecond SLA for AI inferences, which is fundamentally incompatible with our general purpose data pipelines due to protocol overhead. The current batch processes, which scale in a dramatic way, causing the arithmetic intensity of the metric multiplications to increase, but that also inflates the cache footprint, which causes issues regarding balancing compute utilization with the memory bandwidth that is available. Memory access energy is actually more today than the energy spent in the mathematical operations by the transformers and CNNs. And lastly, power efficiency. We all know the data centers needed to build are 565 terawatt hour as our AI workloads scale. So there is a physical limit of this grid capacity, which makes performance per watt, which is also known as tokens per watt, an ultimate constraint. So what is an ASIC? ASIC is the application-specific integrated circuit. GPUs, CPUs are also ASICs. With ASIC, you have advantage of very high density logic, where systolic arrays, custom MAC units, matrix multiplication convolution units can be easily built, but they are all algorithm specific. So the trade-off is once a ASIC chip is built, the algorithm is fixed,
Any algorithm evolution or model update requires a new chip, which is costly and takes 1 to 2 years to manufacture. When we go to FPGAs are called field programmable gate arrays. These are generally flexible, reconfigurable logic chips where you can reconfigure the algorithm that is used quickly and deploy that algorithm immediately onto the system. But all this reconfiguration comes at a cost where FPGA is not as highly dense as ASICs. So ASICs can be 10 to 100x denser than FPGAs does. Thus, this density limits what FPGA can do. It's better to go for a hybrid architecture where FPGA and ASICs can solve the flexibility versus efficiency dilemma. ASICs provide high speed, power efficient execution for very compute heavy tasks like metric multiplication, while FPGAs add reprogrammable logic to adapt to the rapidly evolving AI algorithms. Thus, future-proofing evolving models and the balance between peak efficiency and adaptability is achieved by using both FPGA and ASIC in tandem. Now let's go. How would you partition your workload between an ASIC and FPGA? The traditional AI pipeline can be easily mapped to an FPGA and ASIC. Any pre-processing, cleaning algorithms, experimental operators, even smaller model specific variants can be put on FPGAs. But very heavy operations like inference pass, converged implementations, they can be done on ASIC. Common implementation or algorithm partitioning, where algorithm can be partitioned between ASIC and FPGA using software, hardware, co-design framework. Pre and post processing of data can be done on FPGAs, like for high frequency trading or medical streaming. It can be the data incoming can be parsed, compressed, or formatted before being fed to ML models. Now, once this is done, let's define the interface between the ASIC and FPGAs. How are they connected actually? So the first one is MCM, which is called multi-chip module, where two chips, ASIC and FPGAs, are separate. They are connected through high-speed protocols like PCIe. Then there is system on chip, where both are on a single chip, and this was done by a startup called Flex Logic. They build DSPs on some of their ASIC hard IPs. They were bought by Analog Devices. So DSPs would do the heavy lifting of image processing, while ASIC accelerated their AI workload. Chiplet is more on the chiplet is used for die level packaging, where one die can be FPGA, other die can be an ASIC. Thus manufacturers can have various combinations on how to do it. And the last one is on-site versus off-site approach. FPGAs can be on-site for all the initial sensor data processing application, and heavy lifting can be done by ASICs off-site, as in data centers. This is a basic memory architecture. We have L1 cache, L2 shared cache, L3 is the DRAM and HBM, and L4 is off-chip DRAM or SSD. Some of the design principles that need to be taken into consideration are on-chip buffers. They are very scarce, so they need to be used efficiently. FPGAs also have on-chip memory, but again, efficient use is required. The DRAMs that are stacked can be placed closer physically to reduce the latency. The memory shared between FPGA and the AI compute power needs to be coherent, so that there is no data loss because of mismatch caching. So those type of decisions are very important for the architect to consider. These are communication protocols. PCIe is very well known host to FPGA protocol. CXL is a protocol which is based on PCIe, which allows cache coherency. So FPGA can safely, easily access data on chip. And silicon photonics, I guess we all know that photonics is now also playing a major role in accelerating everything. So these interfaces between chip to chip are actually becoming photonic rather than copper based. I'll quickly go to performance benchmarks. So ASICs are the best performing devices compared to GPUs. Startups like they are claiming that there are massive performance upgrade of 10x over industry leading GPUs. So hybrid definitely has advantage of higher throughput because everything heavy lifting is done by ASIC. Latency is also reduced in a hybrid implementation. Energy is less, and sure. So I'll quickly go over this energy graph. If we keep CPU as baseline 1, pure ASIC will give you 20x. GPU is only at 4x. Then the question is, why is GPU leading the AI revolution? The answer is vertical integration. GPUs are nicely vertically integrated, but there are some startups who are doing this, trying to solve the vertical integration problem. These are some of the targeted domains. Cloud interface, autonomous vehicle. Tesla is already doing this. They have FPGA programmable logic with ASIC neural network. Robotics, NVIDIA has a project going on where they're adding FPGAs to their ASICs. Financial services, JP Morgan, everyone, and those financial companies have hybrid systems with FPGAs and ASICs to accelerate the matrix operations. This is a general framework for architectural decision on what all to consider to decide between ASIC and FPGA. So key takeaways would be how to partition based on what can be done on ASIC and FPGAs. Define your memory architecture, because that is a very critical part, how memory will be shared between ASIC and FPGAs. Then figure out the integration topology, either chip on chip or offsite approaches. And then lastly, hybrid delivers near ASIC efficiency with higher flexibility. Thank you. Any questions, concerns, please go ahead.
Thanks, Gaurav. I can go next. Sure. Sure. Thank you. Okay. Yeah. Hi. Hello, everyone. My name is Narendra Reddy. I work as a lead software engineer at Prudential Insurance Company of America. And thank you for giving me the opportunity as a keynote speaker in this forum. So today I'm going to talk about how to design AI-ready enterprise platforms. I know some of our earlier speakers touched upon the similar kind of subject, but I'm going to share my perspective how to design these AI-ready enterprise platforms, which means like how to building the governance, auditability, and regulatory compliance into enterprise software delivery. So the software engineering is undergoing its biggest transformation in decades. So the generative AI dramatically accelerates development, but speed without governance increases enterprise risk. So if you look at the below, the transformation, it was started as a traditional development and then moved to cloud native, and later on, DevOps or DevSecOps has been introduced, and then later on the platform engineering, and now the AI assisted engineering has been introduced. So AI changes how software is built. Um, I'm going to talk about a framework which is REDM, Regulatory and Enterprise Deployment Model, changes how software is governed in the coming slides. So enterprise, what are all the challenges enterprises are facing in the current AI era? So basically, the AI accelerates software development, but enterprise delivery platforms face growing governance and compliance challenges, which means because of these latest tools Claude or Cursor UI, the development has been exponentially increased faster than expected, but at the same time, the governance models or compliance are not implemented at the same speed in order to deliver the developed product into the production. So we, in the current structure, we have like a fragmented pipelines, different teams use inconsistent delivery process, and the manual audit prep, like evidence is collected manually whenever is required, and the security and compliances. So the policies are applied inconsistently across the applications, and developer experience. So the complex onboarding slows innovation. Like in the current model, if any innovation, if you want to onboard, right now it is complex with the current system. So the traditional CI/CD improves delivery speed, but a regulated enterprises requires governance, traceability, security, and auditability by design. So we are introducing a REDM framework, which is a regulated enterprise deployment model, which is comes with a governance by design. This is a reference architecture I'm sharing with you for secure, auditable, and AI-ready enterprise software delivery, which comes with governance by design, automation by default, and evidence by construction, and AI readiness. So REDM framework integrates governance, automation, and evidence generation and AI readiness into unified enterprise delivery model. So in this slide, the reference architecture I'm sharing, developer experience, which integrates with the CI/CD quality gateways, and then that connects with the security and compliance, which eventually produces artifacts and release management. And from there, infrastructure as a code, which picks up those artifacts and then deployed into the cloud platforms, and then observability and AI governance. So REDM embeds governance and security, traceability, and AI readiness across every stage of this software delivery lifecycle. So coming to this slide, how we can implement as an industrial implementation. So this enterprise implementation, like a Fortune under regulated financial service environment, I'm talking about this the implementation pattern. So whenever like a developer commits a code, basically, which let's say a GitHub Actions picks up that commit, and it goes through the security scan, vulnerability checks, code quality, test automation, test coverage, and all those things. And if it pass those quality metrics, and then the next phase is it build that code and then generates an artifact and push that artifact into the repository. And after that, a CD pipeline kicks in, which takes that particular artifactory, uses as an infrastructure as a code based on your Azure or AWS cloud platform, and then it deploys that artifactory into that particular platform. And also it provides monitoring and audit. So standardized delivery workflows, automated security validation, continuous evidence generation, and consistent governance across enterprise software delivery. With this particular pattern, you can achieve all those. So, by implementing this REDM framework in our enterprise, we have observed these business outcomes. Like we were able to reduce our release cycle from 3 weeks to 1 week, and also we were able to faster the onboarding process about 30 to 50%, and less audit preparation, which is 50 to 80%. And we have standardized pipelines across the organization. We were able to build around 11,000 pipelines using this framework, which also reduces the pipeline failures. So the business outcome is standardized delivery practices, improved developer productivity, reduced compliance effort, accelerated onboarding, and established a scalable foundation for AI-ready enterprise software delivery. So, what it means by AI-ready enterprise delivery? So, embedded governance and trust into AI-assisted software engineering. Let's say a developer uses a AI tool to generate a code. Once he check in the code, a policy validation happens, and after that, it has to go through the vulnerability security scans and test coverage and all those things. And it also generates evidence, and after that, that artifactory will be picked up by the CD pipeline and deployed into the cloud deployment. It always do the continuous monitoring. So the key takeaway is AI increases development speed, while this framework, which I am talking about, REDM, ensures every development remains secure, traceable, auditable, and compliant. How can an enterprise adopt this framework? So, a phased approach for evolving from traditional software delivery to AI-ready enterprise platforms. So, the first stage is standardize common pipelines, shared templates, and then second step is like secure integrated security quality gateways. You have to implement quality gateways in order to stop any vulnerability pushing into the. Yeah, I'll be closing in few seconds. Yeah. And then governance comes into the picture, and then platform engineering, enterprise adoption, scale, and then trusted AI assisted software delivery, AI ready. Thank you. So the bottom line is AI can accelerate software delivery, but the framework which I talked about, REDM, ensures it remains trusted, secure, auditable, and ready for the future. Thank you. Or
Looks like all right.
yeah, thanks. Over to you, Rishabh, or whoever wants to take over. Thank you all.
Thank you.